Hi, in this class we will be studying resonance effect and directive influence of functional group. Benzene is C6H6, and if we try and elaborate the structure of benzene, there are 6 carbons, each attached to a hydrogen, and all these bonds are sigma bonds. Now, each carbon is left with one electron, which tends to form a delocalized pi electron cloud, which generally is represented as a circle. So, if somebody is going to ask you which are the 4 bonds of this carbon, 1, 2, 3, this is the 4th bond, which is delocalized pi electron cloud. When we write benzene like this, each line denotes carbon carbon bond and each carbon is attached to a hydrogen. Say benzene is converted to nitrobenzene. Now, in this reaction, what do you think is being replaced? If you come to think of it, there is a hydrogen over here, and this hydrogen has been replaced by NO2. Now, hydrogen goes in the form of H plus. As a golden rule of chemistry, positive replaces positive. So, NO2 plus attacks benzene, removes H plus. So, in nitration of benzene, from benzene if nitrobenzene is formed, these reactions are called electrophilic substitution reactions. First, you have to be very clear with this term. Electrophile means positive or electron deficient. If positive replaces positive, those reactions are called as electrophilic substitution reactions. In benzene, these reactions usually occur because benzene loses its H plus. Since this is a positive species, it can be replaced by a positive species. So, I hope this is clear. First is the structure of benzene, and secondly, the most common reactions of benzene are electrophilic substitution reactions, in which the H plus of benzene is replaced by the other electrophile. Now, say this is any group X, anything OH, NO2, this is hydrogen of benzene has been replaced by an X. Now, 2 points which are next to X are ortho, next to ortho on both the sides you have meta, and there is only one point which is opposite to X, that is called para. These are not absolute positions, they are relative positions. For example, if I take chlorobenzene and I put Cl over here, then these 2 points, the neighboring points, these are ortho, these 2 points are meta, and this one will be para, and this ortho, meta, para is generally used in common naming. Now, we will look at ESR, electrophilic substitution reaction. We take phenol, this is treated with dilute nitric acid. Just to make you understand the topic, I have written nitric acid as HNO2. Now nitration happens in this case, and the products are nitro at para position and nitro at ortho position. So, nitration of phenol, which is an example of ESR, the nitro group attaches itself at para in this case and ortho in this case. This means the H plus either goes from this point or this point, and NO2 plus comes instead of H plus. Now, instead of phenol, in second example, we are taking benzaldehyde. Now, if we add dilute nitric acid, nothing happens. In this case, we have to use concentrated nitric acid in presence of concentrated sulfuric acid as catalyst and heat. Then ESR happens, nitration happens, and nitro comes at meta position. In this case, nitro is coming at meta, in this case it is coming at ortho and para. So, this class is about these reactions, why in case of phenol the reaction is easier as compared to benzaldehyde, and why in case of phenol nitro is attacking at ortho and para position, whereas in case of benzaldehyde it is coming at meta position. If you are able to give these two answers after watching this video lesson, then the purpose of this class will be met. Now, this is an important class, this is very important as a topic, you must pay full attention now. Molecules like phenol show the phenomenon of resonance. Resonance means delocalization of electrons when the position of the electrons is not fixed. When you cannot pinpoint the position of the electron, that phenomena is called as resonance, and the structures that we draw are resonating structures. The actual molecule is in between those structures. When we take the molecule of phenol, oxygen has 2 lone pairs of electrons, it has total 6 electrons, 2 have formed bond. So, it has 4 non-bonding electrons, which means 2 lone pair of electrons. Now, we will try and draw resonating structures of phenol. In the first structure, the top double bond, try and make it on your right side. So, This is your first structure. This lone pair on O is given to the ring. So, this gives the electron over here. Now, if this will give electron over here, then this carbon will get 5 bonds. Come to think of it, it already has 4 bonds. So, if these electrons of oxygen come over here, this carbon will have 5 bonds. That is not possible. So, as soon as oxygen gives this electron, this pi bond undergoes heterolytic fission. So, the second structure, you must pay full attention to the second structure. Double bond O, one lone pair is left, H plus minus, just look at this structure. Oxygen has given its electron over here. So, instead of single, this becomes a double bond, and this pi bond undergoes heterolytic fission. So, these electrons are over here. Now, this will be minus 1 because this carbon has gained only 1 electron. In this bond, this one electron it already had. So, when heterolytic fission occurred, it got 1 more. So, it is minus 1. A lot of students think it should be minus 2. It is not minus 2, it is minus 1. Now, next, this carbon shares these electrons over here. This bond will break and this will come over here. Now, this carbon already has 4 bonds. Look at it, 1, 2, 3 and 1 is with hydrogen. So, when this carbon shares the electron over here, this carbon will have 5 bonds. As soon as those 5 bonds are break, this undergoes heterolytic fission. So, the third structure is like this. You do not change anything at the top, it is double bond O, one lone pair H plus double bond over here, double bond on this side, negative. So, this is your third structure of phenol. Now, this carbon already has 4 bonds. You understand, 1, 2, 3 and 1 is with hydrogen. So, when this gives the electron over here to form a bond, this will undergo heterolytic fission. So, the next structure would look like this, fourth one. You do not change the top, double bond O plus lone pair H, double bond over here, double bond over here, lone pair and minus. So, if you look at structure 2 and structure 4, they are very similar. It is a difference of left and right. Now, again the last structure, this carbon gives the electron over here and oxygen tends to take back its electron. So, you will have the last structure O, it has withdrawn its electrons. So, again we will have 2 pairs of electrons, double, double, double. If you look at structure 5, it is very similar to structure 1. In structure 1, the top double bond is on your right side. In structure 5, the top double bond is on your left side. Barring that, everything is same. So, structure 1 matches with structure 5, structure 2 matches with structure 4. Now, the actual molecule of phenol is in between these 5 structures. The structures which you can see are called resonating structures, the actual molecule is in between these and is called resonance hybrid. So, we do not know the actual structure of phenol, but we assume that the actual structure of phenol is in between all these structures. Now, you come to think of it, imagine there is NO2 plus, the electrophile. Imagine you have NO2 plus and you give freedom to NO2 plus to attack on any of these 5 hydrogens of phenol. Now, think of it, NO2 plus has to attack amongst these 5 hydrogens. Positive replaces positive, but positive always attacks a negative site. Now, in phenol, where do you see negative charge among these hydrogens? First, in structure 2, it is at ortho, this point. In structure 3, it is at para. In structure 4, the negative is again at ortho. So, these are negative points of phenol. NO2 plus attacks at these points and replaces H plus. So, you must understand positive replaces positive, which is electrophilic substitution, but positive will always attack on a negative site. Why phenol undergoes electrophilic substitution at ortho and para position? Because ortho and para position of phenol have negative charge. Now, look at this reaction. This was nitration of phenol. These were our products. Nitro was at para or ortho. So, if you are asked why electrophilic substitution in phenol occurs at ortho and para positions, your answer is simply because of resonance in phenol, and when a group is giving electrons to the ring, like in this case, this is called plus R effect. So, why phenol is ortho para directing? Simple answer, because of its plus R effect. I hope this is clear. Now, in phenol the reaction occurs very easily. If you recall, here we only use dilute nitric acid and the reaction happened because these points were electron rich, this and this. So, nitro was willing to attack on this, you did not require any catalyst or anything, it happened very easily. So, two things about plus R, because of plus R effect, the electrophile attacks at ortho and para and it activates the group for the reaction. So, phenol wants electrophilic substitution to occur because it carries negative charge at ortho and para positions. I hope this is clear. This is very important and you have to practice to draw these structures multiple times, then only you will be able to perfect this. Now, we will come to the second case. Benzaldehyde. Again we are going to draw its resonating structures. So, top double bond on your right, carbon has no lone pair of electrons. Instead of giving lone pair of electrons to ring, it tends to withdraw electrons from the ring. So, this carbon pulls the electron over here and this oxygen pulls the electrons like this. This is opposite to what you studied in phenol. This is minus R effect, withdrawing electrons from the ring. What will be the next structure? double bond C O, 3 lone pairs instead of 2, and a negative sign. There is a positive sign over here. So, this is your structure number 2, positive at ortho. This positive withdraws these pi electrons. Now, this carbon has no effect of this. Instead of its double bond on this side, it will form a double bond on this side. So, this carbon will not get affected, this one. So, the next structure will be like this. Double bond C O negative H. Now, this withdraws the electrons from this, same, this carbon will not get affected, the meta one. So, the next structure again just like second structure, double plus double bond C O, 3 lone pairs and negative. So, again structure 2 matches with structure 4, and the last structure, this withdraws the electrons from here and oxygen gives back the electrons. So, it will come back to structure number 1. C double bond O H, now oxygen has 2 lone pairs. So, structure 1 matches with structure 5. When a group withdraws electrons from the ring, the effect is called as minus R effect. Now, again we will visualize the same situation. Let us say you have benzaldehyde, there are 5 hydrogens, they have to be replaced, H goes in the form of H plus. So, this is typical ESR, and you give freedom to NO2 plus to attack on the ring, these 5 hydrogens. The first thing is NO2 plus will be repelled by the ring. Why? Just look at these positions, they carry positive charge, positive repels positive. So, NO2 will be repelled by these hydrogens. Now, that is the reason why the reaction in aldehyde was occurring under drastic conditions. It will not happen with dilute nitric acid, it requires concentrated nitric acid because CHO has deactivated the ring. Now, NO2 has no incentive to attack on the ring because this ring has positive charge spread like this, positive. Now, you use the catalyst, you use high temperature and you force it to attack on the benzaldehyde molecule. Then also it will not attack at ortho and para positions because they carry positive charge. Look at these structures, they carry positive charge, but meta does not carry positive charge. So, if you force NO2 plus, it will attack at meta position. So, what we infer from this, groups showing minus R effect are meta directing and deactivating. Why we call them deactivating? Because their positive charge makes sure that the electrophile is repelled, so the reaction is less likely to happen. That is why we call them as deactivating. So, phenol, if you look at this, this was giving electrons. Ring had negative charge. So, electrophile was more willing to attack on the ring, and the reaction occurred at which points? Ortho-para, easily, because ortho-para had negative charge, and because electrophile was willing to attack, we call these groups as activating. It activates the ring. Benzaldehyde on the other hand withdraws electrons from the ring. Ring has positive charge, electrophile has no incentive, so they are deactivating, but if you force them to attack, they will attack at meta position. Now, if you get these two reactions, do you understand the concept why this is occurring at ortho and para and easily? Your simple answer is due to plus R effect. Why this is not occurring easily? It requires drastic conditions, and why then also the new groups comes at meta, because benzaldehyde tends to show minus R effect. This topic is very important. Do practice drawing these resonating structures at least 5-7 times to perfect this. Now, let us see how this is given in your book. There are two different topics. Resonance effect. The resonance effect is defined as the polarity produced, polarity is charge, in the molecule by the interaction of two pi bonds or between a pi bond and a lone pair of electrons present to an adjacent atom. So, in case of phenol, if you think of it, there was a lone pair and there was a pi electron. The effect is transmitted through the chain. There are two types of resonance or mesomeric effect. Resonance is also called as a mesomeric effect. It is written by plus R or plus M. Now, the first one they are given is positive resonance plus R effect. They have given you the example of aniline. In this, N is giving electrons. Look at this, N is giving electrons to the ring. So, the negative is at ortho, then it is at para, then it is at ortho, and the last one should have been the same as the first one. When something is going to give electrons to the ring, then you call the effect as plus R. In second case, they have taken the example of nitro. Nitro is withdrawing electrons from the ring. Look at this, the arrows. So, there is a positive at ortho, positive at para, and positive again at ortho. So, if you tell an electrophile to attack on this, it will not attack, and if the attack has to happen, it will happen at meta position. Now, here are the examples of plus R groups, OH, which we just studied, OR, ethers, or NH2 aniline, which the example is given to you over here. So, these are groups having plus R effect. In minus R, you have aldehyde, which we had just shown, and NO2, they withdraw electrons from the ring. So, you must memorize these examples of minus R and plus R. One important thing I will just tell you, if you draw a benzene ring, the atom which is directly attached to the carbon, if it contains lone pair of electrons, even one lone pair, it will definitely give electron to the ring. That means, if the first atom which is touching the ring has a lone pair of electrons, it will give that. That means, it will be which effect? Plus R. Now, you think of phenol, O, H, how many lone pairs with oxygen? 2, it tends to give electrons. Then you have aniline, it has one lone pair, it will tend to give electrons. So, usually the first atom attached to the ring, if it has the lone pair of electrons, definitely it is going to give electrons to the benzene ring. They will show plus R effect. Now, the next topic related to this is directive influence of functional group. Directive influence means, let us say this group is already attached to benzene, any group, let us call it as N. This group will determine where the new electrophile will come. So, one option, electrophile can come at ortho or para, example phenol, or this group can direct the electrophile at meta, example aldehyde. So, the group which is already attached to the benzene ring is capable of directing the new electrophile at a specific position. This phenomena is called as directive influence. So, if you are asked what do you mean by directive influence of a functional group, the group attached to the benzene ring can determine where the new group will come, and there are two options, either there are ortho para directing groups or there are meta directing groups. So, the first part, ortho and para directing groups, when mono substituted benzene means benzene in which one H has been replaced is subjected to further substitution, three possible disubstitute products are not formed in equal amounts. Two types of behavior are observed, either ortho and para products or meta product is predominantly formed. It has also been observed that this behavior depends on the nature of the substituent already present. That means, the group which is already present is determining where the new group is coming, either it can be ortho para or meta. Now, look at the example of ortho para. They have given the example of phenol. This gives electron, so negative at ortho, then para, then ortho, then back. Look at structure 1 and 5, they are similar. Likewise, structure 2 and 4, left and right, this is the only difference. Now, because the ring is electron rich, electrophile will easily attack. So, these are activating. So, they have written they tend to activate. I hope this is clear. Likewise, if you look at on the other side, meta directing groups, nitro withdraws electrons from the ring. So, there is positive at ortho, then positive at para, then positive at ortho. So, electrophile will not attack on this. If you force it to attack, then it attack at meta. So, these groups are deactivating. So, if you have say nitro and you subject nitro to nitration, add nitric acid, add sulfuric acid, heat this strongly, the new nitro will be coming to meta position. You must understand this, nitro is meta directing. So, these are the examples of all the meta directing groups, NO2, CN, CHO, they are the same. These examples you can put in meta directing, or they tend to show which effect, minus R. And over here you have the groups which show plus R effect. So, plus R effect and directive influence, minus R effect and directive influence, these are similar topics. Why the group is directing to ortho para? Because it is showing plus R effect. Why it is directing to meta? Because it is showing minus R effect. Now, there is one group which has a very different behavior, we will just go through that. Let us say, and this is observed in halogens predominantly, you have Cl over here, chlorobenzene. This will give electrons to the ring. So, what do you call this? Plus R. So, can you visualize the next structure? It will be like this, double bond Cl positive and negative will be at ortho. You can draw the rest of the structures. So, Cl or halogens tend to show plus R effect, that means they give their lone pair of electrons to the ring. So, they should be activating, but they are not activating, they have very strong minus I effect. If you recall, we have studied inductive effect. This chlorine will pull so strongly, this will decrease the electron density of the ring. So, halogens are very unusual in this behavior. They show plus R, but along with that they also show minus I. Due to this, the electrophilic substitution will occur at ortho and para, because these points will be electron rich, but the reaction is less likely to happen because the electron density on the ring has decreased. So, they are deactivating. So, normally ortho para groups are activating, but halogens are ortho para, yet they are deactivating. If you are asked why they are deactivating, you are supposed to write because they show very strong minus I effect. So, this is written over here. Aryl halides, halogens are moderately deactivating because of strong minus I. I hope this concept is clear. Draw these resonating structures, and this reaction and this reaction, the logic behind these reactions, why the specific products are formed, why this occurs under milder conditions, this occurs under stronger conditions, you must understand this concept. I hope this is clear. In case you have any doubts, you can always ask me. Thank you.